There's a picture of stuff, guys. Does this help?
All right. Anybody tell me what this represents? I use some letters up there, which hopefully.
Multiples of one another.
Oh, I love it. So the function, and we're not going to suddenly start to do algebra right now, don't worry, but the rule would be double these. Now, based on your gut, would you say there's a one-to-one correspondence? What does 1 correspond to from this set? 2. And what does 2 correspond to from this set? 1. One-to-one correspondence. 1 only goes to 2, 2 only goes back to 1. Maybe? Maybe. All right, so I'm not going to get too deep into algebra stuff, but this is kind of like where you started talking about what isn't a function would be if I had 3 going to more than one thing. So that wouldn't be one-to-one correspondence, which is actually a little more restrictive than just a function. That's enough algebra. Okay. So this is the idea of domain and range, right? But we don't have to look at them as domain and range. This is the set of 1, 2, 3. This is the set of 2, 4, 6. And there's a one-to-one correspondence. I like it. So another way to kind of think more surface level of one-to-one correspondence is, do they have the same number of elements? Does it make sense? If 2 sets have the same number of elements, then you can find a one-to-one correspondence between them. Let me stop for a minute. Is everything cool so far? Okay, I like it. I like it. Let's see. Yeah. So let's say, all right, sure. This is set D and this is set R. Is D equal to R? Are they equal to each other, the sets? Hell no, of course not, right? You guys with me? 1, 2, 3 is not equal to 2, 4, 6. Correct? Okay. No. But I can use a different symbol to recognize there is a one-to-one correspondence. D corresponds to R. And again, some of these symbols have different meanings. For example, we normally think of that to mean something like approximately, right? But in this sense, in sets notation, it is corresponds to. There's a one-to-one correspondence between. I like it.
Like it a lot.
Yeah, exactly. Now, so let me ask you this: if A was A, B, W, and B was 1, 2, 5, 6, is it correct to write this?
No.
I see a few people telling me answers. Anybody else? Yes? No? Is it correct to write that? Is this correct? Is it correct to write this? Are you guys all right? You guys all right? No. Yeah, it's not correct. I love it. So you guys are okay. Because one quick way is on the surface level, they don't have the same number of elements. So there can't possibly be a one-to-one correspondence. I like it. Okay, so that's not that terrible of an idea. It's pretty straightforward. I like it. Yep. Okay. Now, here comes an idea I referenced earlier that sometimes you've had some experience with. So let me throw this up here so you guys think. What is this kind of thing called?
Venn diagram.
Yeah, good. So this is a Venn diagram. Okay, I like it. Now, let me see if you guys can remember some notation stuff. Don't say anything. Can you write notation that would represent this region? Don't say anything. Just write what region 1, what notation would represent region 1 using this, and the correct set notation. Think about the bouncers, right?
Okay.
The mean bouncer and the nice one. All right, who's got that? What symbol would you use to capture just this region? It's not A, right? But it's A. You can tell me the English word. And B. And what does the and look like?
The mean bouncer.
Yeah, it looks like the mean bouncer. No. What's the symbol look like? Yeah, it looks like an A with that lost the A and lost the bar in the middle. It's a beautiful way to remember that.
Yeah.
So that is the part that represents A and B, because the only way to get into this set is if you are in A and in B, and those are the only things that are in both. I like it. Now, let's get a little tricky. What about if Jeff had more colors available? Come here, holy crap, what are you guys doing? Great. What about, what would represent, how do I want to say this? Yeah, okay, I like that. All right, let's see if somebody realizes this is pretty straightforward. Anybody understand what I'm trying to capture there? Anybody can give me, it should be a single letter with an extra little thing attached to it that describes this. Right? Now that I'm doing this, I'm like, did I even tell you guys about this? That would be so evil.
We didn't see
You
it.
guys tell me the answer
We didn't
that I
see it
didn't
in
tell you.
class, but it's in the book.
It's in the book, okay.
Yeah.
Do you remember what it is?
Yeah, it's the straight bar over the.
Yeah, so this means B complement, or the complement of B. It doesn't mean you're telling B that, hey, you look nice today, but it's complement is kind of like what fills it in, right? The opposite of B, in a way, right?
Everything except.
Everything except B. I love it. Okay.
Yeah, we didn't see it last class, but.
Okay. I couldn't remember exactly because I kind of skipped around a little bit. One little thing about these Venn diagrams, we'll do some more of this here in a minute, but this region out here, let me draw this again because there's too much going on up here. This region out here, like, what is this? What would that, can anyone tell me anything about that element right there?
It's an outlier. Or.
Not really an outlier, no. That's
Or
more of a
not
statistical
the specific
thing.
dot, or like the whole.
Yeah, any dot in there really, but that dot right there, it could have been anywhere, right, outside.
Okay.
So is it an element of A?
No.
No, so it's not an element of A. Is it an element of B? No. Okay, so this entire box we call the universe. I like it.
Yep.
And I think last time, did I tell you about, I don't think I did actually. Do I have it written down to remind? Yes, I do. Okay, we'll get to that. So you have the universe, and then you have subsets of the universe, and they can overlap or not. So if two sets do not overlap, so if I have a universe and I have two sets that are like this, we call these disjoint. Good Lord, Jeff. You made one letter with S and J. Disjoint sets. I like it. Not disjoint, that joint, but not joined. You doing all right, little dude? Yeah? Okay. All right, so let me give you a more concrete example of what I mean with this U business. So if U is the set 1, 2, 5, 8, 11. Let's say A is the set 2, 5, 11. And B is the set, what do you got, Jeff? 1, 5, 8. Let's try to construct this picture. I might move you over here. It's an exciting part of the video. There we go. I like that. Well, would this set actually look like? Am I going to overlap the sets? So they're not disjoint, correct? Why?
That's five.
Yeah, 5's in both. Good, so there's got to be some overlap there. So what we just said, what makes sense to start with? What should the first number I put down be to be careful?
5.
Yeah, so it kind of makes sense to start at the innermost. So 5's in both, so 5 goes here. So does A have 5 in it?
Yeah.
Yes, and does B have 5 in it? Yes, cool. So what goes here? 2 and 11. And of course, what goes here? 1 and 8. And does anything go out in the universe?
11.
Nope, good, I like it. If there would have been like a 13, that would have been out here. Is that cool? Okay, I like it. I like it. Okay. Not too bad, right? Nothing too bad yet. Okay. Let's see. Blah, blah, blah. Oh, sweet. Okay, so they're over there. Okay. I can use those same sets to talk about the difference of sets. So let me ask you this real quick. Let me see. Are there any left-handed people in here? Anybody left-handed? That's intriguing. Okay. Statistically, that's fine, I think. Small enough group. Is there anybody in here who's been out of the country? Anybody? Okay, I like it. I like it. All right, quite a few of you guys. Anybody not been out of the country? Do that for me. Not been out. Okay. So what if I have you, and you? Right? You're a set of people, and I say I want to take away from this set the people that have been out of the country. Right? How many people have been out of the country? Quite a few, yes? But if I'm just looking at this set and I say subtract all the people that have been out of the country, who would I take out of there? Yeah, and you would be left. Yes? I'm sorry, I'm not pointing. No, you've never been in that. No, sorry. Left-handed would have been easier, but so I really want this to make sense. This gets a little weird when you first see this idea, because you could start to think, I'm trying to subtract from this more than it has, but that's not what's important. So for example, if I said, what is A minus B? Are there things in B that are not in A?
Yes.
Yes, but this doesn't care. If I have set A and I take everything away from A that is in B, what am I left with? You can do it. A currently has 2, 5, and 11. Now take everything out of there that's in B.
2 and 11.
2 and 11. Is that cool?
Yeah.
And you guys see where there might be some weirdness, because this has got freaking 1, 5, and 8, so what the hell do 1 and 8 do? Nothing. They don't matter. Just like everybody else who had been out of the country, you guys weren't involved in the discussion because you weren't in the original set. Is that very cool? Okay. Let's see, where am I here? 2 and 11. Okay. Not too bad. Not too shabby. Okay. All right, here it gets interesting. There is a very strange little idea known as the Cartesian product. And by the way, while I'm doing this, I'm going to say this possibly several times this semester. I think I already alluded to this before. We're going to discuss and do things in this class that your students would never do. Yes. Because hopefully this, now here, a little story about Jeff. When I went to college, I wanted to teach high school algebra. That's all I wanted to teach, right? Because I had been tutoring it forever and I loved it. So I went to college, I'm like, I want to teach algebra, and they said, all right, we're going to take calculus then. And I was like, what? I just want to teach algebra. Now, of course, now I freaking love all the shit, but at the time, I'm like, I just want to teach algebra. But when I took calculus, some things from algebra made more sense to me. because a lot of stuff we do in algebra is actually based on calculus stuff in the background, right? So if you're gonna teach anybody anything, this kind of makes sense, hopefully, you've gotta know a lot more than anything you're actually gonna tell them. Right? Because then that's the only way you can have a bunch of tools to figure out another way to explain something, is if you have this bigger perspective of it. Okay. I like that. Every now and again we're going to be doing some really weird shit in here. I'm going to remind you guys, this all relates to this. They're never going to do this weird shit, but you got to kind of get a grasp on this so you can see how to help them with what they're doing. Okay. Cartesian product is denoted by something that looks very familiar. What's different here is that looks like multiplication, yes? What's different here is an operation on sets, not numbers, right? But what's curious is it does have a connection with multiplication. So what the hell does this mean? What this means is I want to create all the possible subsets of two elements from one and one from the other. So like all the possible points that I can make between the two sets. So for example, can I make the point 2, 1? Yes. What else? 2, 1.
2, 5.
And
2,
and then you can also make 5, 1. And is everybody right? Is everybody got me?
Yeah.
And 5, 8. And 11, 1. And 11, 5. And 11, 8. And there you go. Now how many elements are in this set? 9. And how many elements are in A? How many elements are in A? 3. How many elements are in B? And 3 times 3 is 9. So that is the kind of side notation. That's the kind of like, well, that's sort of maybe why this looks like a multiplication symbol, because it actually is a interesting, different way to define multiplication. All the possible pairings you can make. That's a little freaky, all right? But that's all this means is, do I want to say that? Like, do you guys understand, like, set A is, what's a good word I can use here without getting too weird? First degree, like, set A is singular things. Set A, can they live on a number line, for example? 1 dimension, yes? A cross B, 2 dimensions now. If I wanted to plot these, obviously I would need good old XY, right? If I did A cross B cross something else, that would be 3-dimensional now. Dude, thankfully we're not going to do a lot of that because that could go drive you a little insane. Okay. Not too difficult, but definitely different than you're used to. Okay. So let's look at, yes, I like it. Did I want to do that? Oh, I did that. Oh, so weird. I used almost the same numbers. Let's look at a Venn diagram problem and really see what's important to construct it. So what I want to do, okay, so I'm going to give you a Venn diagram that's already been created. I'm going to ask you questions based on what you can see in it. Then I'm going to give you a little worksheet, and you know, worksheets are going to be the thing in here, so just get used to it. To do a problem, one problem is going to be creating your own Venn diagram. So here is, let me see if I can write big enough, likes mushrooms, likes pepperoni. Okay, so I got 20, 15, 4, 11. Okay. Anybody here like mushrooms on your pizza? Or in general, I guess? Yeah, pizza, yeah. Anybody like pepperoni? Anybody not like pepperoni on their pizza? Yeah, okay. Anybody like anchovies? How about ham and pineapple? If it's there, I'll eat it, but I'm not gonna order it. It's there, hey, it's pizza. So let me ask you a few questions. How many total people like pepperoni on their pizza? Say again, sir?
15.
I can almost hear you.
15.
Nope.
35.
35 total like pepperoni, yes? What do these 20 people like? Both. And what do these 15 people like? Just pepperoni. So how many total people like pepperoni? 35. Do you see the number 35 in here explicitly anywhere? So if I asked you to create a Venn diagram and I said 35 total people like pepperoni, does 35 have to actually show up in your diagram? No. Does that make? That's one of the most confusing things when I ask you to create a Venn diagram, like start blank and create it, is people think every number is supposed to show up somewhere. No, 35 does show up, it's just split. Yeah?
Cumulative, right?
Yes. 35 total like pepperoni. How many like both mushrooms and pepperoni? That's an easy one. We already said that. 20. 20 like both. How many don't like either? 11. Kick ass. Okay. Now, okay, good. So let me give you this.
That's the anchovy population. 11.
See, this question only, so who could like anchovies? Any of these people. Does that make sense? Because this only asked about mushrooms and pepperoni, so I'm not going to go that far, because could these people like anchovies? Yeah. They weren't asked, so we don't know, right? Okay, I like it. Let me give you this, and you might want to, so I'm going to have you do like we did before. I want you to work alone a bit first. If you want to, you can start with the last one first, because that comes right up to what we just talked about.